Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're very happy to have Larry Samuelson here from Yale. And thank you all for coming out for an extra seminar this week. It shows what a popular speaker you are, that on the Friday before Christmas, you get a pretty good audience. So he is going to talk about incentives for experimenting agents.
Thank you, and thank you for coming. This paper is joint work with my colleague Johannes Horner. This paper brings together two sorts of things that I have wondered about and worked on for a long time. One is I have a long-standing interest in repeated games. We have some wonderful theorems characterizing primarily the sets of equilibrium payoffs in repeated games. We know quite a bit less about equilibrium behavior in these games. When people use repeated games in applications, they typically have a pretty strong intuition that some of the equilibria that we have available are more interesting, more sensible, reasonable, plausible, you can fill in that blank with your favorite adjective, than are others. But we don't have a very good understanding of what makes them sensible, reasonable, plausible, or other. And in particular, we don't have a shared understanding of what the principle should be for making that judgment. One of the notions that comes up over and over again is some idea of simplicity in general, and in particular that often takes the form of looking at equilibria that are stationary in repeated games, or that are Markov equilibria in dynamic games. And so one of the themes in this work is the implications of stationarity, or the comparison of what we can achieve in stationary and Markov equilibria and what we need non-stationarity for, or what new sorts of possibilities open up when we consider such equilibria. One idea of how restrictive is this commonly used notion. The other branch of this is I've long been interested in prices, how they're determined, how they allocate resources, what form they take, what they depend on, and has especially been interested in the prices and markets when there is asymmetric information or even markets for information. This naturally arises out of the study of repeated games, where attention turns to cases where the monitoring is imperfect, so that you get private information on either side of this relationship. It gives rise to all sorts of puzzles. How do you sell a good which in the extreme has the property, if you identify it, you have just provided everything valuable about the good? This is going to look at a little piece of both of those. Those are problems that are too big, at least for me, to do all at once. And so we're going to look at an example and see what features of those arise. It's called Incentives for Experimenting Agents. So this is going to center around an agent who conducts experiments. The basic setting is we're going to have an agent who has a project that could be profitable, but must be developed through a series of costly experiments. The agent is going to be necessary for this development, but so is funding going to be necessary. The presumption is the agent doesn't have the funding, and so has to seek this from a principal. Now, I want to know, what's the nature of the contract between the principal and the agent going to look like? How would this compare to a case where a single person could both provide the funding and do the experimentation, so that there would be no agency problem? What constraints does this agency relationship place on the efficiency of the outcome, the ability to undertake the project at all? There have to be some constraints if this is going to be a non-trivial problem. These are the ones we're going to have. The first thing is that the agent can't just sell the problem to the principal. Perhaps this is a project that requires some expertise that only the agent has. The agent could perhaps say as many times as the agent wants, to complete this, we have to play basketball like Michael Jordan or dance like Michael Jackson. But that still may not give the principal the ability to do that. Or the informational asymmetries may give rise to such an adverse selection problem that it's impossible to trade this. So that quick fix is just off the table. Both of the parties are going to be necessary for this. In addition, the principal is going to be able to observe.
And that includes also the agent not selling himself plus the project to the principal?
This contract is going to be the closest we can come to the agent selling that bundle to the principal. Okay. So the agent's going to essentially go to the principal and say, I've got a great project, only I can undertake it, you're going to put up the money, and together we're going to get rich. And now the principal's going to say something like, sounds good to me, let's see how we do it. And these next constraints are going to come. Not today are you allowed to that. That's not such a crazy question. Anytime we have an incentive problem like this, we could wonder what would happen if we put this in the context of a market where there might be competition for agents or competition for principals. But we're not going to do that today. The principal can observe something about the outcomes of the experiment, but cannot observe the experimentation itself. So this is a moral hazard problem. The agent's going to come back for the agent's daily or weekly or monthly, whatever the frequency meeting is with the principal, and the agent may say something like, worked really hard this period, got a lot of great stuff done, not quite there yet, no success. And the principal has to think, now, did the agent really do this, or has the agent been in Starbucks all month? And the principal can't tell that apart.
Just writing the software, writing the software.
Yes. Yeah, and writing software, and all the principal can do is the agent can bring a disk or can email a program, and the principal can run it and see if it works. And if it doesn't work, principal doesn't know why not, how much has been done in the meantime. Could be. Yeah, your graduate students come in, you tell them to go do this, they come back, say, no proof yet, who knows? And so the sort of arrangement here is that the principal is going to continually be advancing funding to the agent. The agent is, in principle, continually experimenting. And the payoff here is that if this does become a success, the principal can observe that, you can contract on that. In particular, you can promise the agent a share of
Is it a fixed share, or could that be changing over time? Could there be like a second round of funding or a...
So changing over time is a wonderful phrase here, because indeed part of the outcome is going to be a characterization of the circumstances under which it needs to change over time. Second round of funding, there's going to be nothing like that. Once the first success comes up, we're going to be done. Wonderful. That's the next line. This is still not too difficult a problem. It's a fairly straightforward programming problem if the principal can commit. So what I mean by that is if at the beginning of this relationship the principal can write a contract with the agent that explains the payoff in all of the future circumstances, then we say the principal can commit, and that's not too hard to do. The presumption is the principal cannot do that. In particular, your original contract might specify to the agent, I will fund you for 10 periods, and then if we haven't had a success by then, we're done. Our presumption is at the end of that 10 periods, if the agent comes back and says, how about another shot at this, nothing prevents the principal from saying yes. The principal can say no if the principal thinks it's a bad idea, but if the principal thinks it is a good idea, the principal is free to say yes.
Does he have to keep his promise that he funds 10 periods?
So, no. We're, in fact, going to assume that in each period, the principal can advance the funding to the agent, and they can contract on the outcome of a success in that period. And then the next period, they do this all over again. But the operative thing is going to be that principals can't commit to quit. This, in the end, is going to be what they would really love to do. They would love to threaten the agent with the promise, if we're not good to go by this date, we're done completely. And the difficulty they're going to face is that when that date comes, they're going to have this temptation to keep going.
Not willing to commit to the future something because you don't have any notion of partial progress, or
let's change the question first. It's not a matter of being unwilling to commit to the future, but being unable to commit to the future. The principal would surely be willing if that were possible. And indeed, it is an empty threat. It is the difficulty that you and I can write a contract that can commit us to do certain things, but it's very difficult for us to promise never to write another contract. And that's going to be that's the ability the principal would really love to have, the ability to threaten the agent with the plug being pulled.
I don't get it. Why can't you write a contract that says I'm going to fund you for the next year, and if I fund you any more after that, I'll pay you $1 million?
So,
wouldn't that be the same thing in practice?
no. That's a wonderful suggestion, and let's take an even nicer possibility than that. You will fund me for a year, and if you fund me for anything more than that, you'll pay someone else $1 million, is another version of this that has come up. The difficulty is that there will be circumstances under which these contracts would, by the consent of all of the parties, be renegotiated. In particular, you have funded me for the year. If we had no contract on the table, you would like to go another year. And you're thinking, boy, this is maybe not such a good idea now because I'm liable for this $1 million. At this point, you go to the recipient of the $1 million and you say, remember that $1 million you might have gotten if I'd kept going? You're not going to get it because I'm not going to keep going. But if you'd settle for a nice dinner, or 100 or 1,000, whatever it takes to buy him out of the contract, we'll tear up this one and we'll write just the same thing. So it is, in fact, very, very hard with contracts like that to create this kind of commitment. I'm not suggesting that there are never circumstances under which people can commit, but that there are interesting circumstances under which especially these commit to terminate ideas are hard to make work.
So is this a theorem or an axiom?
It's an axiom.
It is.
It's an axiom.
I can't imagine it's a theorem. I would have called it an assumption. That's close enough to axiom, we could probably agree on that. This.
There are many papers whose topic has had a conclusion.
I see. It's hard to use a contract to commit. That's what you're asking about. That is indeed a theorem in many papers. I don't know how we could offer a completely general theorem like that, but many, many economists have spent a lot of time looking for ways to create commitment. Now, we don't have a perfect understanding of that because in our ordinary speech, we have the ideas that people are committed to some things and not to others. We used to think that Ronald Reagan was committed to certain things. Didn't have the impression that George Bush was committed to very much, I think. And we think those statements had meaning, but don't have a complete understanding of that. Here, I thought you were asking this cannot commit to future contract terms. That's an axiom in this model. Because of this other work, I think it's not a crazy one. And then I'm going to make this last one more precise, but I'm going to presume that the venture capitalist is on the short side of this market. This brings us back to your question about could we put this into a market. The closest we're going to see in this case is that venture capital is going to be scarce. We'll see what that means. But to put this into the sort of jargon that we're used to, these are the elements that this problem has. Hidden actions, that's the inability to monitor the agent's actions. Hidden information, in one version of this, the agent and the principal may have different beliefs. The agent may know more about this project than does the principal. Learning, in one version of this, we're going to be learning about the project as we go along. And I return to the scarce venture capital. And these are the sorts of things that tend to come up in this literature. And so we have them. Related work like this, I will mention one paper. This is by Dirk, Burgerman, and Ulrich Hagee. And they have a model that is very, very similar to this one. Some differences in the implementation, but the basic forces are very, very much the same. The difference is that in their vision of the market, the short side is the other side. So in their vision of the market, venture capital is plentiful. Venture capitalists compete for agents with development projects. Could be. In particular, in their model, venture capitalists compete away all of their rents in this market. So the venture capitalist gets driven to their outside option. This sounds like a sort of technical change. Sounds like it shouldn't make very much difference. It turns out to make a tremendous difference, especially for the sorts of stationarity ideas that we are interested in. By fixing the payoff on the side of the market that has no moral hazard, that has no adverse selection, you take out a great deal of the richness in equilibrium possibilities. In particular, in their model, all of the equilibria are either stationary or Markov, depending upon what the relevant setting is. If you want to ask the question, what difference does it make whether you impose stationarity on your equilibrium concept? What difference does it make that you restrict attention to Markov equilibria? You don't get that question here. Right? So their model looks at other sorts of interesting questions, but not this one. Preview of the results. Agency is costly. Having an agent run the project for you causes some inefficiencies that wouldn't arise if the principal could do the project himself, or if the agent could finance it himself. That's not a surprise. You could look at lists of papers that would have that. Dynamic agency is yet more costly. So what I mean by that, we're going to allow the principal and the agent to do this over and over again. And that repetition imposes another efficiency cost. This is a little bit surprising, because usually when we think about repeated games or repeated interactions, the specter of the future only helps you create current incentives. In this case, the future can make it more difficult to create current incentives. In particular, we will have cases where if there were only one period in the world, we would run the project. Given that there is more than one period in the world, we're unable to run the project. It makes it too expensive to create the incentives for the agent. And not because of the uncertainty. We will look at this, but
By the way, too expensive for who? What does mean is costly?
So we're going to be looking at the two versions of that. We'll look at the payoff to the principal, or we'll look at the payoff in efficiency terms. So if we're looking at efficiency, costly will mean, is the total surplus from running this project positive? And we'll have cases where it is, where we could do it in a one-period agency problem, but not the dynamic agency problem. Or we could ask, what's the principal's payoff look like? And again, cases where the principal would have a positive payoff in the one-period problem, not in the repeated problem. And this, of course, then makes it no surprise there are conditions under which, if the principal could commit, the principal would put a boundary on this problem.
I do not understand that. One thing, dynamic agency is not necessary in order to talk about that is an empty threat that you cannot do it again. So if it's not that dynamic, then de facto you're saying that you, as the way I understand that, at least so far, would be tantamount to say, if it is one shot and therefore I can actually commit not to do further contracting. So if you want to have the difficulty of further contracting, the way I understand that, at least so far, is that you need to bring in dynamicity or not.
We can certainly talk about contracting difficulties without having a dynamic problem. We can talk about empty threats without having a dynamic problem.
So I thought of it in
Without having a very dynamic problem.
Yeah.
You're working at a bank. Someone walks in and says, give me all your money. You say, why? They open their coat and show they have explosives strapped around their waist. And they say, because I'll blow up otherwise. And you should say, no, you won't, if you think that's an empty threat. So already in those circumstances, we can talk about empty threats. You have to be sure if you're going to say that, but...
No, but I thought the question...
I understand that empty threat arise in an empty world, but I thought the way you phrased the difficulty of the commitment, it was this inability to have a second round.
No, the difficulty of the commitment is the inability to commit to end the relationship. Right.
Therefore, there ought to be a future. What I'm saying, I don't understand. Okay, fine, I will understand.
No, I thought I thought the question was that if I'm looking at a not dynamic problem, a one-period problem,
Yeah.
that effectively it says that I can commit. That we're
Absolutely.
not-
Exactly.
That's what I'm saying.
That's
what he's saying.
Yeah.
Yeah, so that's why I believe I just said that this makes it no surprise that the commitment ability the principal would like to have is to end the project. If there are circumstances under which you can make it go with a commitment to end and cannot make it go in the absence of such a commitment, you should expect that commitment to be valuable.
So, but the question is it the dynamic which is costly or just the fact that you can't commit it?
These are rolled together here. So we're interested in the dynamic in the presence of an inability to commit. Now, let's suppose you could commit. So that is this second item. I'm going to keep the model as it is, but I'm going to relax the sequential rationality constraint. I'm going to ignore it for the principal. So I'm going to give the principal the ability to commit. This makes it a relatively easy problem to solve, and the efficient outcome invariably runs this project at full speed. I'll be specific about what that means when we get into the model, to a point, and then pulls the plug on the project. And so, as we put it, this front loads the agent's effort. And already something to notice about this is this idea of non-stationarity comes up here. The efficient outcome is a pretty non-stationary one. I want to even draw a distinction there. It's no surprise that efficiency often requires a non-stationary strategy or a non-stationary contract. We're familiar with ideas such as in a repeated prisoner's dilemma. You can get a nice outcome. You can get both sides cooperating, backed up by the threat of perpetual defection should anyone ever deviate. And so that's a non-stationary strategy. But it has a stationary outcome. We see cooperate in every period. In this case, not only is the strategy non-stationary, but the outcome itself is. And so that's a little less familiar. Now we put the commitment problem back in. We ask for sequential rationality. This is going to preclude this pulling the plug. Nonetheless, in equilibrium, we are typically going to be able to come, some cases, exactly we're going to be able to achieve that. In some cases, we're going to be able to come closer to that than we can in a stationary equilibrium. we're always going to want to front load the project. And so the general force here is the principal wants to quit early, and the principal is going to do the best within the means available to do that. Time for the model now, so good time for questions. Say.
What did it mean to commit to quit early?
So.
Before the expected time the agent could even finish? Or?
No, because there will be no. There will be no counter for that. Certainly earlier than the agent wants to, but more than that, earlier than you would want to, if you could just take this project over and do the whole thing yourself. So inefficiently earlier. Or suppose you were we call it a social planner, you can call it a dictator. Suppose you could tell these agents what to do. And you would do the calculation and you would find what is the best thing. Take your pick on best. Maximize the total surplus, maximize the principal surplus, and it would be early with respect to that measure.
So the difference between telling the agent what to do and doing it yourself?
When I said he's a social planner, if we maintain the presumption that the agent's participation is necessary for this project, there's a difference in the story. But making him the social planner is just the same as combining these functions in a single agent, in a single person. Here's what the model will look like. There's going to be a project. We're going to have time divided up into discrete periods. We're going to think of this as the experimentation period. How long depends on what interpretation we have in mind here, and I have nothing to say about that. At the beginning of every period, we have a probability Q that the project is good. The principal can advance to the agent a sum C. This is the cost of experimentation. The agent can either pocket that and do nothing, or can spend it on the experiment. This is where the moral hazard problem arises. We always have this temptation for the agent to grab the money and have a nice, easy life for a period. Two possibilities are the outcome of this: success and failure. If the agent doesn't conduct the experiment, it's a failure for sure. If the project is bad, it's a failure for sure. If the project is good, it's a failure with probability 1 minus p. So there's a randomness here. If the project is good, it's a success with probability p. If it's a success, everyone knows that. It yields a burst worth pi. And that ends the agency relationship. The principal, when advancing the cost C to the agent, can promise the agent that the agent gets a share 1 minus s of pi if it's a success. S is a choice on the part of the principal. Doesn't have to be the same in every period. And if it's a failure, we might revise our probability that this is a good project. We might have learned something, and we go on to the next period.
So all these parameters can vary from one period to the next, except for p. In this
Pi is fixed.
Pi is fixed.
So the payoff from a success is always going to be the same. P is fixed. The probability that the good project gives the success, that's going to be fixed throughout. The one parameter, S, is a choice, so you can certainly choose that to be different things. And Q is a belief. And so as this project goes along, you may revise Q. You're going to be a good Bayesian in that respect.
But then you should think that you may want S to depend on Q.
Absolutely. So you may want S to depend on Q. You're going to not be completely free in what S you choose. Every time you offer this contract to the agent, you understand his incentive to actually conduct the experiment instead of pocket the money is going to depend on Q and S. And so if you're going to get the agent doing what you want, S is going to have to depend on Q.
Functional distinction between Q and P?
That's a very good question, the functional distinction between Q and P. I think it's on the next slide. And on one other hand, so let me take that one, and then we'll do Q versus P. I hope it's on the next slide now. Yes?
So we just consider the binary case. Either the agent keeps the money and does nothing, or it invests in the project. But you can think of like a case where it tries but not very hard. I mean, spends some portion of the money on trying to make the thing work, and that affects somehow its success probability, right?
So the obvious alternative would be to let the agent say, choose an effort level in the unit interval.
Oh, but then just
And-
point or something, right?
And indeed, we're going to have some probabilities. There'll be z's coming up in a little while, and you interpret those as percentage of effort, and you'll be on the mark with that. What's the difference between Q and P, or why do we have both Q and P? Because I want to separate this into two possibilities. First, I'm going to set Q equal to 1. We're going to know that this is a good project. The P is still there, meaning even a good project, when we hit the success, is random. So we know this is an idea that's going to make sense, but we know we have to work, and we don't know how soon it's going to come up. So if you're, what was the example, writing a piece of code, you know you can make it work. You don't know how long you're going to have to work on it.
And even if it works 7 years,
So this is one case that we're going to look at. And it's the ability to separate out this case that we have these two. Now I want to ask, what's the efficient outcome? Just forget the agency relationship. Suppose you could do it yourself. Your value from undertaking an experiment. This is the normalized present value. D is the discount factor. So to keep things on an even footing, we multiply current payoffs by 1 minus the discount factor. Probability of a success, payoff if you get a success, cost of the experiment. Discounted future value, probability it's a failure. And you're into the next period facing just the situation you did today. And so that V shows up in the next period as well. Do the algebra. This thing is worth doing if this is positive. So there are two ways of writing that as positive, but the interpretation is, not too surprisingly, expected payoff exceeds cost. Now, let's look at the other case. Suppose Q bar is less than 1. Same sort of situation, but you don't know if this is good or not. You don't know if it is good, how long it's going to take to develop it. And you have some, not very high, but maybe initially small probability that just might be just wrong-headed and is never going to work. So now the value looks much the same. It's a function of Q. Everything's going to depend on your current posterior value. One possibility is to do nothing. We didn't have to worry about that too much in the previous one. Why not? In the previous case, we had this condition for efficiency, and either it holds or it doesn't. If it does hold, you will do this experiment forever, because every period that you face looks just like the other one. You may have been at it for thousands, millions of periods of failure, and you're thinking, boy, this is one of the great coincidences in the history of probability. But you're still ready to go on this. And if this doesn't hold, you'll never do it. Now, whether you do it or not is going to depend on your posterior probability that this is a good project. And indeed, at one point, you might just decide to quit, and so this 0 is always an option there. And now your expected payoff again, normalized value. Success probability is now probability of good times probability of a success times good. Payoff minus cost. Discounted value, probability of a failure. Next period's value at a new belief. This is the function, Bayes' rule, that takes your current belief and turns it into a new belief. A more pessimistic future belief, incidentally. Failure is always bad news here. And so your beliefs are going to ratchet down.
I still only see the product Q times P.
That's right. Indeed. Not only do you only see the product Q times P appear, that's of some interest. Once again, if this is going to be positive, this thing has to be positive. That's the only hope you have. And so here is the condition for success, or this is the condition for undertaking an experiment. And this looks just like the previous condition, except P has now been replaced by Q times P. Another way of putting that, there is no option value in this setting. We're used to, say, multi-arm bandit problems, where you're taking draws from distributions, trying to learn which of these distributions is relatively profitable. And it's a standard result there that you may have an arm whose return you know. In fact, for convenience, make it a safe arm. It always returns the same thing. There's no randomness there at all, and you know that. And you may have a random arm, and your current expectation on that random arm may be that it pays off less than the safe arm. Nonetheless, you may pull the random arm again, because there's option value to pulling that. There's an upside payoff that you can exploit. There's a downside payoff that you can ignore by switching to the safe arm. There is no option value here. The point of this is we're interested in the implications of the fact that this relationship is repeated for the agency contract. It's no surprise that if we have an option value to continuing, that repeating the relationship is going to have some effect on the agency contract. To put it differently, we're interested in questions like stationarity or Markovness of an equilibrium. No surprise that those can fail if we have the sort of information link across periods. We've shut that down here in order to get at the non-stationarity itself. Now we're going to divide this into two settings. The first one, we call them development projects. Oh, I'm sorry, yeah. Yeah.
So QSMT was supposed to be the principal's belief about whether the experiment is good or bad.
Yes. Whether the project, let's call it that, is good or bad.
But then it looks like the project is a success with probability Q sub t times p. Why is that? I mean, why is the principal's belief influencing the likelihood that the project is a success?
If the project is bad, it is necessarily a failure. If the project is good and the experiment is undertaken, it gives a success with probability p. If you undertake this experiment, two things have to be true for this to be a success. It has to be a good project, and you have to get the success draw from a good project. The joint probability is Q times P. I wouldn't use the words exist a solution, but yeah, you have the concatenation of the probabilities down.
Maybe the answer to my question is this is just the principal's estimate of the, not the true value.
Right. Yeah.
I
think that's the answer to the question, because that's his best estimate of whether
we are calculating
we're
calculating the value of a combination principal agent here. There's no agency problem in this version. And so if someone handed you this project and said, do you want to run it? You would ask, what's it going to cost? That's here. You would ask, what do I expect to get out of it? And this is your best guess of what you expect to get out of it. All right, now we're going to put the agency problem in. And we're going to do this in two stages. We'll develop the first one with some carefulness, and then time will cause us to fly through the second one, even though that's the more interesting one, but it's nicer to start with a simpler setting. Let's look at the case where we know this is a good project. Now there's another reason for doing this. We're looking at what impact does the spectra of the future have. Now, in hidden information problems, we know that the prospect of a future can cause difficulties. Most of us have had experience, at least when I asked my classes, have you ever had a job where you were loath to work really hard for fear that if you did, more would be expected of you in the future? And I get most hands up on this. People who respond affirmatively to that understand the ratchet effect. The idea that you have some information, how productive you are, how productive your situation is, and if you reveal that, it can be used against you.
And our aim here is to establish a work environment where that isn't true.
Here, here they know everyone is good. That's why Q is equal to 1. Yeah. And so then you don't have to worry about that. The point is, if we have learning going on and then we discover some intertemporal links, we're not surprised. And so we start with the simplest case. Now we're going to look at equilibria for this, given that we have now the principal funding the agent. And we're going to start looking for the natural things, stationary equilibrium, because every period this problem looks just like it did before. We have the same setting working where if you were doing this project yourself, you would either never do it or always do it. And we're going to look at a stationary equilibrium in which the principal always gets the agent to work. Now let's look at the principal's payoff within a period. We have the normalization factor. The principal offers 1 minus s times the payoff to the agent, so the principal keeps probability of success, principal share times the payoff minus the cost. Now the agent has an optimization problem. Agent could do two things, can work. Normalization, probability of success, payoff, share the agent gets. Plus, discounted probability we go to the future, continuation value for the agent. The other thing the agent can do is just pocket the money. In that case, you get the money this period. No chance of a success. You go to the second period with probability 1 because there's no chance of a success, and so you get this payoff. If the agent is going to work, this one must be at least as large as that one. That's going to be the incentive constraint for the agent here. If we're going to get this equilibrium to work, this is going to have to be non-negative. The principal's not going to do it if the principal loses money in every period but makes it up in volume. And this has got to be at least as big as this to keep the agent from cheating.
Discounting, or maybe it's the other way around.
Delta,
has to be less than 1.
delta is going to be a number between 0 and 1. We want it to be greater than 0. If it's 0, there is no future, and we're kind of out of business on this. We will typically want it to be less than 1, because if it is 1, then some of these calculations are not going to converge. There are going to be places where we're going to divide by 1 minus delta, for example, and people will get after us if that's a 0. And this is the statement, delta less than 1, that other things equal, you would rather have things today than tomorrow. Maybe not a whole lot. Delta might be very close to 1. And indeed, we're going to do much of our work in the limit as delta gets arbitrarily close to 1. But we're always going to start with delta less than 1 and then let it get very large.
This must be a stupid question. I can't figure out the answer. Why can't you have an equilibrium where the agent never does anything?
So I'm finding an equilibrium so far.
You're not claiming it's the only one.
No, we will, by the time we're done, we will have all the equilibria. There, in some cases, will be equilibria in which the agent never does anything, but not always. So in some cases, in particular, if this inequality holds, there will be no equilibrium in which the agent does nothing. And the reason why we would propose such an equilibrium, and now we would ask, are we both behaving optimally in this equilibrium? If I'm the principal, I could offer you the money to conduct the experiment. And you'd say, why are you doing this? I loaf all the time. I'm just going to pocket this. And my response would be, no, you won't. I'm offering you such a generous payment, 1 minus s times pi, that in fact you will find it more valuable to work than to take the day off. And under these parameter values, it will be worth it to me to induce you to work. Actually, in terms of constructing equilibria, it would be wonderful if there were always an equilibrium in which the agent never worked. Because that would be an equilibrium that would give us each a payoff of 0. That's our mutual min-max payoff. There's nothing worse we can do than a payoff of 0. And if we had that available, then we could do all sorts of tricks in terms of constructing equilibria. And what we would do is use that as a threat that if we don't do the right thing, we switch to this bad equilibrium. So whenever you're looking for the best equilibrium in a game, the first thing you do is ask, what's the worst thing that can happen? And if you find a situation where the worst thing that can happen is mutual min-max, then this is a time for celebration. This is worth chocolate chip cookies or something like that, because that makes things much easier to do.
Less interesting.
Now, a comparison. This is the usual sort of benefit-cost ratio compared to probabilities. This is where I'm willing to start talking about things. So let's measure that ratio over here. This is pi over, that's not the world's greatest C, but this is pi over C. There's a boundary sitting here, 1 over p. This is the efficient boundary. The efficient solution is never experiment down there, always experiment up here. Now, the bound we have up here, there's 2 over p, and then there's 2 over p plus delta over 1 minus delta. Our condition for this equilibrium in which the agent always works is that you have to be up there. This much I would call simply the agency cost. If we were in a one-shot relationship and we had to get this agent to work, we couldn't do it unless the probability is up here or higher. And the basic idea behind that is the agent always has the opportunity to just pocket the experimentation money. In any outcome, you have to give the agent a payoff at least C. But you have to pay the experimentation money. So without the agency relationship, the efficiency criterion for experimenting is expected payoff exceed the cost. With the agency relationship, it's expected payoff exceed twice the cost. That gets us up to there. And yet this equilibrium we just constructed requires more than that. And this is what I would call the dynamic agency cost. The specter, if we had just a single period and our probability was sitting here, we could, and indeed we would, induce this agent to work. If there's a future going on and we want this agent to always work, we have to be up there. Now, what's behind that? We'll see what's behind that in just a moment. Let me fill in. What about an equilibrium in which the agent never works? There exist such equilibria, those in which the agent never works. These are down here. If the probability is below that, there's no way you can get this agent to work. And this follows just from a characterization of this agent's incentive constraint. And this will show us where the dynamic agency cost comes from as well. So here's the taking the day off payoff. You pocket the current payoff, you go and get your future value. Here's what it takes, what you get from working. Probability you get a success, share you keep, probability you go through and get your future payoff. Now, look at the probabilities on the future payoff. If you shirk, you get to the future for sure. If you work, you run the risk of a success. And if you get a success, there's no more future. The future is less valuable if you work than if you don't work. That makes it harder to get this agent to work. And the larger is W. The larger is W, the more expensive it is to make this agent work. And so the reason, given that there's a future out there, that you have to kick up the success probability in order to get this agent to work is because this agent looks at that future and says, I'm not willing to work anymore under circumstances that I once was willing to work. And you have to pay him more. And if that's going to be worth it to you, if you're going to cover that cost, this project has to be more valuable. This is a basic trade-off that's going to come up over and over again. The more lucrative is the future, the more expensive is the agent. And the agent is because work risks success. Yeah. Absolutely. Yeah.
Suppose it's going to be true the value of the
Delta is a parameter. That's fixed.
from the view of the
Let's not call it a probability. Delta is a discount factor. It's a measure of preferences. It's how these agents trade off the current period payoffs versus future period payoffs.
From the view of the agent.
And the principal, they share the same delta. You could make their deltas different because it's maybe a bit of a coincidence that they have the same delta. It surely gets more complicated. In particular, make their deltas different, and now not only do they want to run this program, but they want to borrow and lend to one another. The high delta person would like to borrow money from the low delta person. And if they could, they would structure this contract to implicitly have such borrowing and lending in it.
Never work because they want to do that forever.
Of course, which we just
Yeah.
did, right?
So that one...
He said you convert every corporation into a bank, which we kind of just did recently.
Yeah, indeed. Indeed. So employment contracts would have elements of banking relationships in them, and we're getting, closer to that.
We got pretty close to that recently, right?
So we're not going to do that because we're going to have we want to have a simple life. So down here, the contract's null. Up here, you can make the agent work. The question is, what's in the middle here? We were a little surprised to find there was a middle, but there is. This slide just tells us, explains why we have the null contract down there. We're going to skip this slide. In the middle, here's the sort of Markov equilibrium we do in the middle. You're going to come to work, and your boss is going to flip a coin. And instead of heads and tails, it's going to be work, no work. And if it's no work, you're out on the river. And if it's work, you have to work. This is the counterpart of scaling this project down, putting in only half effort instead of full effort. And so we're often going to talk about this as working at half speed or not full speed. Now, what this is going to do is decrease the value of this project to the agent. And why is that going to be valuable? Because that's going to make it cheaper to get the agent to work when you want him to. The agent, understanding that in all the future periods it's only half-time work, views those future periods as less lucrative. It pushes down this value W, and that relaxes the incentive constraint for the worker. And in this region, this is the only way to make the worker affordable. Tell the worker's going to work full time, and it's too expensive to pay him to actually get him to do that. We've no threats yet, but that's a very good suggestion. So far, we're just looking for stationary equilibria.
I could sort of say, if you don't work really hard, then I threat by making you half-employed and make you work sort of only.
In fact, you'd love to do even better than that. Threats in a couple slides. Now, we can do the calculations for this, and indeed, we can solve for the various values. I don't think we need these details. This is our summary of the Markov equilibria. On this axis, we're measuring our usual measure of how valuable is this profit. It's payoff if a success divided by its cost. Thick line is the principal's payoff. Dashed line is the agent's payoff. These are the null projects down here where nobody gets anything because you can't create any work. And sitting down here someplace is the efficiency thresholds, where you would be able to do this project if you could combine the two agents, but you can't do that. Up above here, these are the full speed equilibria. The agent's payoff is constant on these full speed equilibria. You're paying the agent enough to make the incentive constraint work, and no more than that. And the principal's payoff goes up and up and up as this project gets more valuable. These are the partial work equilibria in the middle. Here, the principal's payoff is 0. Has to be, because every day the principal flips a coin between work and no work. What's the payoff to the principal of no work? It's 0. If this flip is going to work, the two payoffs have to be the same. You can get someone to mix only if they're indifferent. Otherwise, if you walked in and the company was flipping a coin and they really wanted it to come up heads, you can bet you'd see a lot of heads. And in the company and say, well, you know, even random coins come up with streaks ahead sometimes. So principal's payoff is 0 here, and the agent steadily rises. As you move up, the agent can work more and more. So these are the payoffs from the stationary equilibria. Now,
this is a really good way of looking at it.
yeah. Threats. Threats, he said. So we're going to have threats. And we're going to break this up into these 3 regions. This one down here is straightforward. There's nothing you can do down there ever. Having non-stationarity doesn't help you very much. We're going to look up here. This is where we're going to spend our time. And then this one will be straightforward. The payoffs up here from the Markov equilibria. So we draw a picture of that. Let's put W down here, V down there. The efficient frontier looks like that. And our Markov equilibrium, or our stationary equilibrium, picked out one point on this frontier where the agent gets C, gets just the cost of always grabbing the money, just enough to make the agent work. And the principal gets something I'll call V star. And now we want to look at what's the best sort of non-stationary equilibrium we can get here. First quick lemma that we won't go through, though, is that this is out. Agent can never get more than that. And why? This is related to this question, could you have an equilibrium where the agent never works? And the answer is no, because you would pay him enough that he would want to work. What's the most you have to pay him? It is exactly this. This covers the agent's effort in an equilibrium in which the agent always works. That's the most lucrative future this agent's ever going to see. So you never have to pay the agent more than that. Given that you can pay him that and get this, this is the lower boundary on the principal's payoff. So all this is out. And the action's going to be up there. And in particular, we can ask the question, could the principal do better with a non-stationary equilibrium? We're going to build this up in 2 stages. One, we're going to talk about threats. The equilibrium path is still going to be stationary, but we might threaten the agent with bad things if the agent doesn't do the right thing on the path. And in the second stage, we'll actually get to this front-loading of effort and these non-stationary off-path beliefs. Now I'm going to work with another mixture here, but not the same sort of mixture as last time. This time, when you come to work, your boss is going to hand you the coin and say, you flip it. This is what we're going to refer to as using a public randomization device. Or another way of saying this is, you're going to look at the temperature when you come to work, and if it's even, you work that day, and if it's odd, you don't work that day. The point behind this is you can verify the mixture and not just the outcome. And so the principle is publicly going to mix between working and not working, partial effort again, if you want. And should there ever be a deviation, you show up and the principal says work. You say, no, this is an odd temperature day, I'm not supposed to. And the principal says, we decided work anyway. Then you switch to the threat. And what's the threat going to be? This outcome here. In terms of the principal, that's the worst thing the principal can get. And so this is the worst we can threaten the principal with. This gives us an equilibrium as long as this mixture gives the principal a higher payoff than V star. Because if it does give the principal a higher payoff than V star, the principal won't want to renege on this behavior and get punished by switching to here. Now, how could the principal possibly get a higher payoff than V star, the always work equilibrium, by not having the agent always work? And the answer is, it makes the agent cheaper. So when we talk about this equilibrium corresponds to setting Z equals 1, no matter what the temperature is you work. We talk about having you work less, 2 things happen. The total surplus goes down. less likely this project's going to be a success, and so less likely that we have any value at all. But the agent's future gets bleaker, and so the agent is cheaper. And this might be a good deal for the principal. You might prefer this project not be as valuable because it makes your agent cheaper. And everything hinges on how valuable the project is. If the project is really, really valuable, you're not going to want to give up anything on this. And making the agent cheaper is not going to be worth it. If the agent's only a little bit valuable, if the project's only a little bit valuable, it's going to be worth making the agent cheaper. And so, you sort of hate to make yet more categories, but there's going to be a dividing line like this. And up here, this is going to buy you nothing. And the best you could do is just sit on this outcome. Down here, as z decreases below 1, there's going to be a payoff path that looks like this. This part of it's irrelevant, because that makes the principal worse off. But up here, we have circumstances where making the project less valuable makes the agent enough cheaper that it's worth doing. And indeed, our set of equilibrium payoffs, we're eventually going to fill in this whole little lens here. So this little lens now is in this. And in particular, now we're going to really have some threats. This turns out to be the worst equilibrium for everybody. Bad for the principal, bad for the agent. If I want to know what's the best thing I can do, these are the calculations. If I want to know what's the best thing I can do, it is described here. I can save you some reading. Best projects we can get, the frontier projects here, the surplus maximizing projects, in every period.
Best for the agent, best for the principal, or best in terms of overall efficiency, or?
You get your choice on that. So what I mean by that is we are characterizing now this frontier. If it's best for the principal that you want, you take this point on the frontier. If it's best for the agent you want, you take this point on the frontier. If it's efficiency, you take the intersection of an off-diagonal with the frontier, which happens to be that point again. Have some other weighting. If you're a social planner and you weight the principal at 2/3 the value of an agent, you get a point that looks like this. Whatever your criterion of best, it's on that frontier. And the way to get that is by an equilibrium that in every period, once again, flips a coin, and heads is the agent works full time. And tails is we switch to this worst equilibrium and stay there forever. This is the counterpart of the pulling the plug that the agent would do if the agent had commitment power. If the agent had commitment power, the best equilibrium would be we work full speed for some number of periods and then we're done. There's no done here. There is no equilibrium in this case where we're down here. This is the closest to done you can get. So the best equilibria are we work full speed for some amount of time and then we switch to this somewhat more gentle way of life. And then we're there forever. Now again, the interesting thing about this is we now have non-stationarity not only off the path but on the equilibrium path, even though this looks like an inherently stationary model. That is correct. Because it is an equilibrium to do so. So not commit means take any history of play, any combination of events that got you to your current circumstance, and your continuation play must be an equilibrium of the repeated game. Now we are designing the equilibria that give us the nicest outcome. We're allowing ourselves that freedom.
Why wouldn't I jump back to that point? I don't understand.
Why?
That would give me more, and I mean, so we are in this committed.
Why
my point is now we are there committed and I go, you know what, we would both be better off if we jumped there, so let's just not do the thread.
I'm going to take that in 2 stages, a kind of facetious one, and then I'll just avoid it. The facetious one is because it is an equilibrium to stay there. That's the difference between saying we're committing and saying we're looking at equilibrium continuation play. Now, the second part is you are essentially suggesting a yet stronger equilibrium concept, one that's commonly called renegotiation proof. We say that an equilibrium is renegotiation proof is if, should we ever find ourselves with a continuation path that is inferior for both of us to an alternative equilibrium continuation path, we will renegotiate to the equilibrium continuation path. We have not asked for that here, and if we did ask for that, this equilibrium I've just described would not be an equilibrium. Yeah?
So, you know, when the answer to some of the questions was we'll stay in a certain place because it's an equilibrium.
Right.
Now, you can ask about whether it's a stable equilibrium, and that's a more reasonable question in the real world. So you think about some kinds of perturbations. You know, somebody gets sick or something, and so that's a perturbation on the system. So they're not working even though it's an even weather day or something. And you can ask whether that'll tend to drive you away from that equilibrium or keep you in that equilibrium. And I think that would be a reasonable thing to ask about these equilibria.
We have not looked at a version of this with perturbations, but we have much, much better chances of surviving that than his renegotiation proofness. Important to recognize that this is a sequential equilibrium. Sequential equilibrium is a user-friendly version of perfect equilibrium, which is a perturbation-based equilibrium.
Which is a stable equilibrium,
we kind of shy away from the phrase stable equilibrium.
Well, because it's stable to what?
Yeah,
right.
Yeah. In our view, usually the word stable is already built into the word equilibrium. And what sort of stability you want depends on what equilibrium concept you have.
In physics, we talk about stable and equilibrium, 2 perturbations, but whatever it is.
So I missed that last sentence. It sounded a little slippery, actually.
No.
I knew you couldn't get through a talk without handing you
What would be the fun in that?
No, the perturbations that you're talking about are saying if there were these small perturbations in the probabilities of beliefs or something.
Mm-hmm.
But that's but Jennifer's notion was a perturbation in the physics sense that if the system got shocked in people's behavior, that's not so obvious that the thing you're talking about is stable in that sense.
No. So did not say.
Just that he has a better chance against.
Did not say that we had done that.
No,
I observed that some.
You might have thought that. I just thought I would clarify.
I don't think anybody but you thought that, but and I don't think you really did. But you notice time's running out, and you haven't had a chance yet. But okay, we will go on.
Could you just remind me again, what is that point over there on the left?
That is the worst equilibrium
How do you get there?
for both the principal and the agent. And you get there by choosing the appropriate value of the work flip. Work on even numbered days, work on prime numbered days, whatever you would like, by choosing the appropriate value of the work flip. In particular, this equilibrium corresponds to the case where you always work, decrease the probability of working, and first, that makes the principal better off, always makes the agent worse off because he's not working as much, and since the future is less lucrative, you're paying him even less when you do ask him to work. So he takes it on the chin 2 ways. And so initially you're doing really well because he's getting cheaper, even though you're giving up some surplus. Eventually you're giving up lots and lots of surplus, your value starts to dive, and when it just hits the place you started from, that's the lowest payoff we can inflict on the agent, lowest payoff we can inflict on you, and that's the lowest work probability we can sustain, and that's what gives us that worst stationary equilibrium. Now we're going to piggyback these together That's correct. This with public randomization. Now, in most cases, public randomization is a convenience that can be replaced by more complicated private mixtures. I would hate to do that here, though, so we're just going to have the public ones. And now we use that as the punishment in this sort of non-stationary equilibrium. I already told you there's no action down here. We could talk about this middle case. That's just like this one, except in the middle case, the worst equilibrium really is there. There, you can really commit to pulling the plug. And why is that? In the Markov equilibrium, this is the case where you can't get the agent to work full time. In the Markov equilibrium, the principal's value is 0. Oh. And so now there's a great punishment equilibrium here. Everyone stays home and never does anything. And should anyone ever deviate, you say, okay, you got us. We can't do this staying home stuff. We're going to go to the Markov equilibrium. The principal says, gee, I get 0 there too. And so that looks much like the same case. We put these together. We can write down the proposition, or we can look at the picture. These are the bad projects. You do nothing but sit at the origin there. These are the really, really good ones. You do nothing there but sit at this point. These are the ones that fall in here. And to put that into perspective, to get this to fit on the picture, this is not a 0 here. Instead, you think of this lens being the one that I put there. So it sits up a little bit. There's the Markov equilibrium. This dotted line is a set of equilibria you can get with stationary outcome paths, but using off-the-path punishments to support them. These are the equilibria you can get with the front-loaded effort cases, the case where you work full speed until a time in which you pull the plug and switch to the worst equilibrium. And the point is, if you're a principal here, you surely like those the best. It's even a little greater contrast in this intermediate region here. Because now, there's the Markov equilibrium. And these are the equilibria you get from these front-loaded effort paths. These are really front-loaded because when the plug gets pulled here, everything stops because you have this nice 0-0 punishment value. And here, both agents can be made better off by front-loading the effort. This is the sense in which the principal wants to quit too soon, because when the time comes to quit, the agent would very much like to continue. So would the principal. And yet, arranging the equilibrium this way makes both of them better off. Now, if we had a lot of time, we'd do this all again. We won't do it quite all again. I will show you a couple of...
I have a question.
Yeah.
So these things of front loading, and just like when you do experiments and people actually collaborate much more than sort of game theory would predict, I would think that maybe also here in reality, maybe people might be willing to do things which are more optimal for the project and not do all this stuff. Is that?
So first, though this is a discussion for another time, I would take some issue with the people collaborate much more than game theory predicts. I have not quite the same view of the experimental evidence, but we'll put that one aside. Absolutely, all of this is an equilibrium analysis. And so we are counting here on the players understanding the nature of the equilibrium and actually behaving in that way. Let me go back to the early remarks. The standard exercise in repeated games is not to worry at all about what sort of equilibrium behavior it takes and to characterize the set of equilibrium payoffs. We end up with some equilibria that look sort of sensible as descriptions about how people might behave. We end up with other equilibria that don't, and we'd like to understand the difference. Many of our constructions for repeated games are in fact not real constructions. They're non-constructive arguments about what payoffs could be equilibrium payoffs. I think of this as a step towards characterizing what sorts of behavior is behind this. One of the things we get out of this is we have this penchant for looking at stationary behavior in stationary environments. And one defense that might be offered for that is that in a stationary environment, there is no payoff gain to be had from a non-stationary outcome. At least in this case, that's not true. And so you may still believe in the simple equilibrium, but you must have some other justification for it. So those are the sorts of details we'd be interested in. Now let's throw some learning into the mix. This turns out to be an extra level of difficulty because we're going to have two state variables now, not just one. One state variable is going to be the principal's belief, one is going to be the agent's belief. These will differ anytime the principal asks the agent to work and the agent doesn't do so. In particular, after that, the agent's going to be more optimistic than is the principal. Because the principal will think a failure's just come up and that was bad news. And the agent says, nah, there's no failure. That's the one that's going to be germane, because in equilibrium, the principal is never going to pay the money to the agent and tell the agent not to work. It could, so again, we won't have to worry about this, happen the other way. The principal could pay the agent not to work, and the agent could sneak into the lab at night or whatever it takes and do the experiment, and then the agent would be more pessimistic than the principal. Key thing that makes this work is a lemma, even without having... Oh yeah. Well, then there's no hiding that, at least in this model. That's right. So if he, and so
you can hide the fact that you work,
but not a success. That's right. We could imagine other circumstances, lots of variations you could do, but this is the one that we have, and that's why anytime you work, again, you risk success, and that's always a consideration for this agent. The key technical device here is that there is some linearity in the agent's value function that lets us handle the two state variables. I suggest we not worry about the details of that. This is the same sort of incentive constraint for the principal. There's grabbing the money now, being able to continue for sure, working now, being able to continue with the probability that you don't get a success now. And so same force here. High continuation values make the agent expensive. We now have, with the help of that linearity, we're going to convert this to a one-dimensional state space, which is QT, the posterior probability of the principal, that this is a good project. And the principal's behavior is going to be conditioned on this. So we're not going to talk about stationary equilibria, but Markov equilibria. Equilibria in which behavior depends on the current posterior. And following up what we learned from the previous case, there are going to be essentially two phases of behavior. Principal has the agent work full speed. Agent's incentive constraint binds. Principal gets a positive payoff. That was the counterpart of the equilibria that we had up here. Principal has the agent work at less than full speed. Principal gets a zero payoff. That's the counterpart of the equilibria we had down here. And now the principal's task is to use these building blocks to attach them to these different values of Q, however you would like, to make this agent work. Unfortunately, we have even more cases than we did before. We can talk about how valuable is the project. That's lucrative versus not so lucrative. I call these lucrative, these intermediate. These have just disappeared completely because who needs another line in this table? And we can talk about how fast are we going to learn? How fast does a string of failures drive us down this posterior space? That's going to depend on P. Here's where the difference between P and Q shows up. The larger is P, the worse news is a failure, and the more rapidly will you be shooting down this space. Now, if you go down this space very rapidly, that means the agent doesn't think there is much of a future. There's a cliff sitting here, and if you fall off of that cliff, there's going to be no more experimentation. You can only get so pessimistic before which you're essentially in this region here, and there's nothing you can do. If the posterior is going to move quickly, there's not much future there. And accordingly, there's not much scope for trying to make this agent cheap by reducing the future value. If you're going to be moving slowly down here, there's a big future there, and it's really tempting for this agent to try to keep this future going. This agent says, pretty good gig here, lots of years of sitting in a lab, and then you may want to do that. Given the time, we skip all the analysis. Here are what the Markov equilibria look like in this picture. What is it? On this axis, we measure Q. This is the posterior probability that this is a good project. If you're a principal, think of this as the further you are to the right, the more likely is this project to be good. These are the principal payoffs for 3 cases, at least 1 or 2 of which I will describe, as a function of the posterior. This one, for example, this is a lucrative, fast learning project. Now, what do we know there? Principal's payoff is always positive. That means of these 2 building blocks that I talked about, agent works full speed, principal gets a positive payoff. Agent works partial speed, principal gets a 0 payoff. We're always in the work full speed version here. That's because this is a pretty valuable project, and we don't want to use the surplus burning feature of less than full work to make the agent cheaper. Notice, however, that this curve is not monotonic. It dips down up here. That means for this principle, a higher probability that this is a good project is bad news. If you were this principal and you could burn some probability, you would do it. Because a high probability that this is a good project means lots of surplus for this agent. That means that makes the agent expensive. And so this agent comes to you and says, this is a really, really good project. And the subtext there is, I'm really, really expensive. And if you had that agent and another agent who says, I've got a pretty good project, and the subtext there is, I'm not so expensive, you would take the other one. Indeed.
It's pretty high up there.
That's right. Now this, but though we could make it turn earlier if we chose different parameters. This is a more severe case. This is another fast learning project, but only an intermediate one. And so here, if this project gets really good, this agent becomes too expensive to bear. And so you're stuck here switching to the partial work equilibrium because he's too expensive. So if this agent comes to you with a really good project, that's worth 0 to you. And if you, again, had 2 agents come to you and one says, I know my project's good, and the other one says, probability 3/4 it's good. Your payoff's higher with the probability 3/4 that it's good. And it is because that makes him cheaper. Now these are the Markov equilibria. Absolutely.
And I thought it varied with time.
It does. So we're talking about the prior. We're talking about the probability when the agent walks in the door. So now, indeed, as time goes on, Q is going to be drifting down here. And in fact, if you're in this blue situation, and this agent walks in and the prior's up here, your expected continuation value is 0. Should you get down here, your expected continuation value is positive. And so, well, at the beginning, the principal's expected value is 0. So this doesn't give him any solace. But should he get here, the principal says, boy, am I glad we had these 100 failures. Because now I have a positive expected payoff.
Right, so he's motivated to play with value 0 rather than just saying, screw it, I'm not going to do anything.
Oh, no. So that he is not, because his value really is 0. There's a good event here that gives him a positive payoff. There are other events that give him negative payoffs, and his expected value is 0.
So what motivates him to play?
In fact, nothing.
Okay.
So he gets to this point by burning some money, which is not going to
Yeah. So agent shows up there, and no reason for him to do it. One sentence, perhaps. We could do the non-Markov version of this. It would reverse this picture. We would again have that we would front load effort all of the time, and it would always be valuable to have a higher prior on the principal's part. So the monotonicities would go away, and some of these, here you are slack at the beginning and work at the end. That would turn around. You would always work at the beginning and be slack at the end. So we could do all that, but we've done enough, so I'll stop. Thank you. Yeah.
So how do these results compare with the Burgerman results? They have a market for principles. They have a market for principles.
Their results are essentially these. So no, that was a terrible thing to say. Because if we look at the principal's payoff under their results, I can draw that for you. And that's this. Because their principal always earns a 0 payoff. The principal has no information to earn money on. The principal has no effort to earn money on. The principal is driven then to indifference with the principal's outside option. Now the reason I said their results are essentially this, which was a bit too quick, is that as a result of this, there's nothing to play with in constructing equilibria in their model. Once you found the Markov equilibria, you have found everything. To put it yet differently, there's no real agency. Though they have a principal and an agent, there's no real agency problem in their model. There is an agent who has a programming problem to solve. But that agent knows there's a fund of money available as long as he preserves this 0 expected value. He has to be clever in making sure he preserves that. But given that he does, then we're set. That's a good question.